I'd like to thank the organizers for this very nice workshop and also for inviting me and giving the opportunity to present my work. So in case you were wondering, this is my university here. This is just a research agency that funds the thing, and this is the Institute of Physics and symbol, okay? So, and these are my collaborators. Balázs Posgai, whose name was already mentioned lots of times, so you might be familiar. And this is Yunfeng Jiang. Last time I checked, he already moved to Southeast University, Nanjing, but when we did this work, he was at CERN. And this is my PhD student, David. And these are the two papers which contain the work what we did. This was ready by the time, the original timing of the workshop. And this is something that we did afterwards. So this is the outline. So at first, I would like to talk something about TTbar, the motivation of the CDD problem. Then I would like to introduce factorization formula, which will be the cornerstone of establishing the connection between these different subjects. So actually, the subject will be mostly spins, some fields, which is the TTbar, and a very, very little bit of strings, just mentioning. Okay? So this factorization formula establishes basically the connection. I talk about long-range deformations. And then it turns out that we can break this nice integrability, but in a very interesting way, which is, I think, is very novel. And it was discovered partly by a group with Benjamin Doyon and other people in it, and partly by us. This is the weak breaking of integrability. There are a lot of questions about this still. And then I will present my conclusions. So let's start with some motivation. So we have exactness matrices, and we normally have an embarrassment of riches. And people don't really talk about this, but we consider a scalar theory, single scalar, and parity invariant. Then we have this general possible polynomial Lagrangian. And if we just impose that there is integrability, which means that particle number is conserved in scatterings, then we find that there is a single way to tune these couplings, which leads to actually what is called the Singe-Gordon model. And there is actually a very nice review of this by Patrick Dory in exactness matrices, which was a talk he gave at the school in Budapest, actually. And then we know that for this theory, we have an S matrix, which is actually just a single CDD factor. We know the exact correspondence between the parameter of the CDD factor and the coupling. But in general, such a CDD factor S matrix can be just any product of these brackets, these ingredients, and this is called the Cdd ambiguity. So basically, we have an infinite parameter family of possible S matrices corresponding to a single scalar particle which has no bound states whatsoever. These are chosen in such a way that there are no poles in the physical strip, so there are no bound states. And the question is, where is the implied infinite parameter family of QFTs, right? So you would think that probably these are all bona fide S matrices of some integrable QFTs. So the idea that actually, I will quote later, Smirnov and Zamolodchikov, who actually invented this. But so for any QFT, which you define by any action, you can consider two conserved currents. This is not related to integrability, although normally you only have two independent conserved currents. Well, not really. But for the TT bar, you have two independent conserved currents and you don't need integrability, right? So there's an actual example that's here. So, and then you define this sort of anti-symmetric combination of two currents. For example, you can take the energy current and the momentum current in any relativistic field theory, and then you basically what you compute, this combination is determinant of the energy momentum tensor, which can be written in this way in complex coordinates. And then you define a deformed theory in such a way that you define that you basically think about adding this operator to the action, but in a certain way, that you consider the derivative of your action to be the integral of this operator, which is also deformed under lambda. So what you do at first order, you add it, you compute what happens, then the currents are still conserved, but they are deformed up to order lambda. Then you put it back at order lambda squared, then you define the deformation, but then you have to correct the currents with order lambda squared, and so on and so forth. So in the end, what happens is that you still have conserved currents, but their explicit form depends on lambda. So that's an interesting way of defining a theory. And then there is an interesting fundamental factorization formula which lies below the integrability of these deformations, or the solvability rather. If we consider the theory in an infinite Euclidean cylinder of spatial circumference L, then the TT-bar operator, which I just defined, actual definition is a little more complicated. Okay, I don't go into all sorts of details. The expectation value of this operator in any non-degenerate energy state of energy and momentum can be written in a factorized form. It's very strange. You use actually, it's a very nice proof by Zamolodchikov, which uses translational invariance and clustering properties and some OPE considerations. So this is a very involved proof. But you have this very nice identity. But then basically, once you know this expectation value, then you can compute the energy levels deformed by this by perturbation theory to any order actually. And the idea is that all these expectation values are related to energies and momenta of states. So you know these expectation values, you know exactly, because these are just giving you energies and momenta of these states. So what you get is that the deformed and finite size energy levels is satisfy the implicit Burger's equation. That's familiar from hydrodynamics, where lambda is time, L is position, and here is some external force given by the momentum of the state. So if this is, you are considering zero momentum states, then the solution is extremely simple and you can solve it by the method of characteristics. And then, here is the paper by Smilov and Zamolodchikov where they actually show this. And what happens is that the S matrix, the scattering matrix, is also deformed, and we know how it is deformed. I think Changrim showed this formula before. But this is just a special case for TT-bar. I'm going to give you the explicit formula, the general formula later. Because in integrable QFT, you can do much more. So the first thing is, this is for non-integrable QFT. If you do the TT-bar deformation, and you know the solution in principle of your QFT, then the TT-bar deformation can be computed from this equation, right? So if provided you know the undeformed QFT solution, you can solve the deformed QFT, which is interesting, I think. But if you have some integrable QFT, then this deformation can be extended to a general combination of higher spin conserved charges, as actually Changrim explained, and it leads to a definition of the S matrix by a CDD factor, okay? So this, there is a general function that can appear here, and these alpha S parameters are related by the couplings by which we add these TT-bar, higher TT-bar deformations. And the S runs over the spins of conserved currents. And for Singe-Gordon, for example, S equals 1, 3. So this phi function satisfies that it's self-conjugate under crossing. And basically, it can be any function. You can think about producing any function by this. So basically, you can think about covering the general Cdd ambiguity by these deformations. Okay. There is actually a little problem here that this Burger's equation generally develops shock singularities at some finite L equals L star. And the theory breaks down at short distances, and it's very hard to define what the UV completion is. Changrim actually went in this direction to discuss it. I'm not going to discuss this in particular, but I will return to this at the end in the conclusions. So, but anyway, you have to keep in mind that the status of these theories is not especially clear. So there is this paper by, actually it involves one of my former PhD students who actually looked at this. So an example, by the way, example UV completion is one that was mentioned by Changrim. Tricritical to criticalizing RG flow is the critical endpoint is a TT-bar perturbation. So that's exactly a RG flow that exists up to any energy, because at the UV it flows out from a tricritical point. Okay. So, but all the fact that you can solve these theories and you can give these explicit formulae, they basically rely on this factorization. Okay, next please. I just switch subjects. Okay, just keep this in mind. Switch the subject. So we take an integrable local spin chain. Well, that's a theory that you can imagine. Hamiltonian is sum of some local interaction terms. Like, for example, you can think about the SUN integrable chain, where this Hilbert space is just the product of C to the N over the sides. And the Hamiltonian, local Hamiltonian, is the permutation operator between these two neighboring subspaces. -1 is just convention, okay? And well, this is certain choice of units that I use here, but it's not so important. And the integrability of this chain, but that's just an example. You can consider any local interacting chain. That's usually the case. It looks like this. And the integrability is basically determined by the existence of commuting conserved charges, as many as the length of the chain, basically. And these can be written as sums of local densities. And I choose the index alpha here in such a way that you can imagine, for example, the Hamiltonian here is supported on two sides. So this is basically a length 2 operator in the sense of just involving two sides in each term. So I think about this Q alpha x as being length alpha, so that the subsequent higher and higher charges, they are supported on more and more neighboring sites. And you can give the length of a charge as just giving how long the density is, how many sites the density involves. And they are commuting, okay? As we all know, the Hamiltonian is basically Q2, just considering nearest neighbor interactions here, okay? So that basically covers lots of examples that we know anyway. And then I can define a boost operator. I can define a boost operator to any operator which is given in this form. And it's very simple. If the operator is given as this sum, which is now infinite, so this is actually properly only defined for the infinite chain, okay? It's finite, it's not really easy. Then I can define the boost operator by just adding this up multiplied by the position. And what's interesting is that, for example, also in SUN chain, but many other chains, you can use this boost operator corresponding to the Hamiltonian, and you can generate the charges sequentially from each other. So basically, you take Q alpha, you commute it with the boost operator, you put an I in order to keep it Hermitian, then you get Q alpha plus 1, plus some irrelevant constant that's not important. So that's the boost operator is basically sort of generating the charges from each other in a recurrent manner. And then there are also currents, because I have these conserved charges. If I take the time derivative of their density, which is just this commutator with the Hamiltonian, and this should satisfy some continuity equation, but on the lattice, this is a difference equation, right? So there's a current, this is basically a spatial derivative, or spatial difference rather. And I can also consider generalized currents, because any of these Q can be considered as Hamiltonian, right? Just Q2, any of the Q beta can be Hamiltonians. So I can think about replacing the Hamiltonian here. And this is still a conserved quantity under any of these Q beta because of the commutation relations. So I can have some generalized currents for if I take conserved density alpha and I think of capital Q beta as Hamiltonian, there's a current which just fits in this equation and defines you the continuity, conservation, local conservation of this quantity. All right, that's okay. So now comes the factorization theorem. So this is actually a novel formula on integrable spin chains. It's interesting that no one has thought about this. And basically the way the formula is proven is basically just following Zamolodchikov's paper with some little, it's actually easier because we don't have to care about singular operator products whatsoever because this is all finite. So we don't have to do all the OPE and whatever, but it's a very simple algebraic manipulation. So there's a theorem 1 saying that for any eigenstate psi, if I construct this composition of currents and charges, so this alpha and beta, so there is really two different currents, and actually 4 because alpha beta and alpha beta, right? So it's interchanged. Then this is constant in space. It's actually an easy one-line calculation. You just compute the derivative, I mean spatial difference, and if you compute this derivative, it turns out to be a total commutator with H, but because this is an eigenstate of the Hamiltonian, then this is vanishing. That's actually one of the steps that Zamolodchikov does in the continuum in the field theory when he proves the factorization. Corollary, we use that psi is an eigenstate of all the Q alphas because they are commuting, so I can choose my Hamiltonian eigenstates to be eigenstates of all the charges. Plus I use translational invariance, okay? Plus I also use the fact that this Q is a sum of local densities, and if I just separate them far enough, then they just don't overlap. I mean, in this product, when I have this product, if I take X far enough, then the supports don't overlap, okay? So they just don't talk to each other. Then it's very easy to prove the next step is that this is just equal to this product. That's actually the factorization identity, but then you can a little go a little further, and you can define this K alpha beta gamma X, which is this funny combination of actually generalized currents even. So here I was talking about the Hamiltonian currents, but I can take the gamma Hamiltonian generalized currents, and then the same argument just tells you that this formula holds. Okay, so this is what this is. This is basically TT bar. It's more or less a determinant. Okay, it's actually a determinant right away with the minus sign, whatever. It's like a determinant, just like the TT bar operator. And the point is that in any eigenstate of all the charges, the expectation value factorizes like that. Okay, so that's very nice. So we have a factorization identity. Now, what do we do with that? Okay, so this was derived in this paper. So the point is that we can generate these factorized operators from some generating function. That's also an interesting fact. So that we can make these bilinear combinations of the charge densities with some parameter L here, and you can just prove by explicit computation that this gives you this combination. Just take really the commutator of charges and compute explicitly. And then what you see, L equals 1 case of that generates all the K alpha beta gamma. So actually, if you want to prove theorems about this capital Ks, you can prove for all of them at once by taking the generating function. It's very nice. So these operators actually exist, and they have this factorization property for a general integrable local spin chain. So that's something that I want to emphasize on this slide. So it's not dependent on whether it's SUN or whatever. You take a general integrable spin chain as long as all these manipulations they go through. It's basically what you need is that all these operators are local, and then these manipulations go through. Then you always have this factorization property. Okay, so this is what I told you. That's a novel type of identity. I don't know if it can be useful for other things than the things that I'm doing here, but it would be nice to see whether it can be used for something else to do with spin chains. Okay, it's very nice. So now we try to deform spin chains. So we have this integrable chain, and we try to play the TT bar game. So we have this factorization property, and now we try to do a TT-bar-deformation, so to say, of the spin chain. So the idea is that when we deform, we want the deformed theory to be integrable. So we have some parameter, and we have some charges of the deformed theory which depend on the deformation parameter. And they are supposed to be expanded in a Taylor series of kappa in such a way that at kappa equals 0, I just get the original undeformed charge. They are supposed to commute with each other because obviously I want them to be generate an integrable chain. And I also assume that they are the sum of densities. It turns out that I cannot assume anymore that these densities are local in the sense of being supported just on finitely many sides, but I can suppose that they are quasi-local. Now, if you don't know what quasi-local operators are, there's a specific definition, which is mathematical, but the easy way of thinking about them is that these densities are not supported on finitely many sides, but they have some center, and away from the center, they just decay sufficiently fast. Typically, they decay exponentially in the cases that I'm considering here. So that's basically, they are almost local, so all sorts of things that sums over them and similar things, they do exist, okay? Whenever I compute something, then things are convergent. And for example, if I take two of these densities and take them far apart in the product, then their overlap is negligible, so I can simply factorize their expectation values and whatever. All right. And I also assume that I have some deformation for the eigenvectors of the chain. So the common eigenvectors of these deformed charges can also be expanded as in kappa, and psi 0 here is just the undeformed eigenvector. Okay, and I can now postulate that I can satisfy 1 to 4. Maybe it can be satisfied another way, I don't know. I can prove that this is the only way to satisfy it. But this can be definitely satisfied by postulating that there is some operator x of kappa, that the eigenstates are deformed by this way. So this is basically a generator of the deformation. The charges are deformed by commutator with x of kappa. And because of the Jacobi identity of the commutator, if I take the derivative of the commutator, that is deformed the same way. So if the commutator was originally 0, it stays 0. So I keep this, okay? And this is, and if this is true, it's even one more thing is true, because basically I'm doing here some sort of unitary transformation of this psi in such a way that I'm also similarly transforming the Q with the same. So the eigenvalue of this deformed eigenvector under Q alpha kappa is independent of kappa. It's the same as when I started the deformation at kappa equals 0. It stays the same along with this deformation. Okay. And I mean, probably people from the ADS-CFT community know that there exists something along these lines, right? This is called the long-range deformation of spin chains, which was, I hope I quote the right paper. You can tell me if it is the right one, 2009, Bargir, Beizert, and Lobert. And you can just choose this generator to be a lot of things. So one thing you can choose this generator to be is actually kappa independent. You just take it to be the sum of any local density. It doesn't really matter. It's just a trivial similarity transformation of everything. It doesn't do much to your thing. Then the next thing you can choose this x kappa to be minus the boost operator corresponding to q kappa alpha. You remember that when we are deforming to first order, it's the original one, but every time I go next order, I already have to correct things. So this is sort of self-consistently defined in the deformation. And then if I look at this commutator here, then I just get that this derivative is exactly given by summing the current over the line. I just use this, how the generalized current was defined, but now I extend this to kappa. Kappa equals 0, this was the way to define the generalized current under this Hamiltonian corresponding to this conserved quantity. Okay, so I just expand this definition to any kappa. And I can also use do a bilocal deformation, which is I take this sort of bilinear combination of conserved charge densities, x less than y, and then I can simply compute this derivative just using this formula, okay? Just commutation relations. It's very simple, it's one-line computations. And it turns out that you get exactly this k operators, but this time defined by kappa. So this k was this j, q, j at x plus 1, appropriate indices, but this time it's all deformed by kappa. Okay. And there is also a gauge freedom that you can actually change the Q alpha that I don't want to get into, but basically the densities are not uniquely defined. You can always add anything to the densities that's a total derivative in continuum terms. If you sum up the density, that leads you to the same charge, but I just leave this completely untouched. This is not important for me. So these were introduced in the context of ADS-CFT for several reasons, which I'm not so much familiar with because I'm not an ADS-CFT person, so you probably know much better. But the underlying structure of the factorization relation was unknown at that time. So these were introduced and treated, but the factorization relation wasn't used because actually TTbar-deformation as it is, it had not been published in 2009, so it wasn't there. So nobody would have thought about making the connection. So then you can think about, next thing you can think about, you have an integrable spin chain, then you have beta ansatz. Now things can become a little more complicated because it depends on the volume, okay? So let me take first infinite volume. So if I take n particle beta states in infinite volume, they usually look like some sort of bunch of plane waves, and there is some factor here which is just responsible for the S matrix when I exchange two particles. And then the conserved charges have some eigenvalues which can be written as summing over the roots. This lambda n can be thought of as a vector containing all the roots corresponding to the given eigenstate. The roots here are arbitrary because there's no quantization relation in infinite volume. They're just basically some numbers. And this is the momentum. And if I take the boost deformation and I have this property of the charge, it turns out that the all orders in kappa, you can see that the only thing that happens to these states is that this p function gets deformed, p lambda, the original momentum, plus kappa times the original charge density of this deforming q. Actually, here I changed notation from q to h for some unknown reasons. but that's the charge density. No, sorry, that's not the charge density. That's the one particle eigenvalue. That's different. Sorry, that's fine. Just messed up in my mind. This is true to all orders in Q. Now, this was actually realized by Balázs that if you use this, which was known to the ADS-CFT people long time ago, this allows to derive. Well, I should have put the quotes there. The current expectation values in finite volume beta states. That's actually there were already talks about generalized hydrodynamics, right? And the most important ingredient there is that you have to know the expectation value of the current, because that goes into the equation. And that was actually novelty that you discovered, that is the basic, the cornerstone of how this works. And the way it was discovered is basically a conjecture. So Balázs actually went through several steps of trying to prove this, and this was one of the intermediate steps where he recognized that if you take this, all of this at face value, and you take it at finite volume, which is not exactly very precise thing, because if you go to finite volume, your problem is that the kappa deformation order by order makes your charges longer and longer. And at some point you get the wrapping corrections in ADS-CFT. But if you neglect those, you suppose that they are just small and you can take the limits and whatever, which is just an assumption here, then you can use this deformation to derive that formula. So this is not yet the full derivation. Actually, Balázs later gave an actual exact derivation, which is much more involved and uses form factor expansions. But this is where the whole thing started, I should tell you, because what happened was that we had a journal club where Balázs told us about his latest paper, and then he just listed all the properties of these deformations. And then just the night ago, or maybe a few nights ago, I was reading something about TTbar just for fun. And then I looked at the formula of the S-matrix deformations, which I was going to present you, and I said, that looks like TTbar. Okay, so what's the connection? So it was like an accidental thing just coming, two threads coming together, right? So this is the formula. Again, you have the infinite volume beta states. You take a bilocal deformation, and then you can just compute that this leads to a deformation of the S-matrix of this form. Okay. The charge values are independent of kappa, so you can actually integrate this equation exactly. That's very easy to integrate it. It's just the first order term is already exact. You don't have any higher order corrections. And if you remember, in the TTbar in QFT, you have this. Actually, there was the Singe factor, but you have this. It can be written in this way. So you have this formula here, and that's actually the same shift here. It's absolutely the same sort of shift, okay, for the TTbar in QFT. And then, but the point is that something was missing. What was missing was the factorization property wasn't known on the chain. If you know the factorization property, then this is actually a theorem that these two are related, okay? But that was what we actually computed. Then you can go to finite volume, and you can do, as I told you, valid up to wrapping corrections. So what you say is that it's a tricky thing to consider. You have this kappa deformation, it works to any order. What you do is that you go to order n, and you consider charges which are not too long, so that you can take a volume which is large enough to contain them. So it's a little tricky to say what you are doing here, but basically the idea is that you always stop at finite order, finitely many charges in such a way that then you can take a large enough volume so that there are no wrapping corrections, okay? And you have this, then you have this asymptotic Bethe-Ansatz formula for the kappa deformed theory with all the usual formulae for the charge eigenvalues, which the charge eigenvalues are given by the same H gammas as before. Why this is dependent on kappa now? Simply because the quantization condition for the roots is dependent on kappa. It's not the charges which depend on kappa, it's the root, the allowed values of the momentum or the beta roots which depend on kappa on the deformation. And then you can actually compute how this depends on kappa. And then there's a very nice proof which I don't actually reproduce here, but you can read in the paper. It's a few lines of simple manipulations, but it's long. But the thing is that you have three statements, is that these deformation rules, they are true. Second statement is that factorization holds for the finite volume beta states. Third statement is that the current expectation value is given by this nice formula, where this is just if you imagine that this is a beta space, it has roots lambda j, j goes from 1 to n. Then you have this current, which is the current of the alpha charge under Hamiltonian beta. You make a vector of the h alpha values at each root. You make a vector of the derivative of h beta values at each root, and then you sandwich them with the Godin matrix that actually comes from the beta ansatz. And then this is actually the formula that is now proven, and that can be used to prove then the GHD current formula in the infinite volume limit and continuum limit if you want, if you wish. And the point is that if you assume any two of these, then the third one follows. Now, actually, now we know that 3 is a theorem. 2 is already a theorem because I proved this. So now we know that all of them, all the 3 are true. Yes?
Is this matrix symmetric?
Yeah, it's symmetric. It's not obvious that under JK exchange symmetric, but if you compute it, yes, it's symmetric. Yes. It's symmetric. Basically, this first term is just non-zero if J is equal to K, and this other term is just the phase shift, and you use anti-symmetry of delta, and then the derivative is symmetric under the exchange of No, this is a symmetric matrix. Yeah, absolutely. So now comes the next thing, is that we have these deformations, and we might want to look a little at them. So whether QFT or spin change, whatever, we can consider that there is some theory space, as we normally talk about, and then there is some subspace of manifold of integrable models, which is a very high codimension subspace. We know they are very special. And if I find some deformation which keeps integrability like this kappa deformation, that's basically a tangent vector. So that means that I found the tangent direction, and if I follow the integral curve, which is defined by the equations, the differential equations that I gave you, that just follows a curve inside this manifold, deforming the Hamiltonian. But now you can play the following little trick, which turns out to be quite interesting. That suppose that you don't follow really the curve. Suppose that you just stop at first order, you don't correct for the higher orders. Then you have a theory which at first order of deformation is integrable, and then integrability is just broken at higher order. And the question is whether there's anything that makes these things special. And what I'm saying is yes. And actually, I would say that probably there are second, third, and other order deformations which can also be introduced, but we stopped at first order. That's already quite complicated when you really want to do the calculations. So integrability is preserved to first order of kappa. So for example, we took the boost deformation, which was generated by this, and then we have the charge qk beta. Q beta is just deformed by the current itself. You just look up the formulas that I gave you. This is deformation order kappa squared. So the first order deformation by a current, just deforming the charges to first order by adding this sort of current, leads to this sort of weak breaking of integrability. And this was realized also by Benjamin and collaborators in this paper, similar, actually more or less the same thing, but not in the same language. Okay, so it's a little different in this TTbar-like language, but this is the idea. So basically, that's like following the TTbar flow only to first order. You don't correct them to the for the higher orders. And right. And so this boost deformation keeps integrability to first order. And I mean, I'm obsessed about this because it's breaking integrability. Because the point is, integrability is nice, and then your system, if you do quantum quench or some non-equilibrium process, relaxes to some generalized Gibbs ensemble. Question is, if I break integrability, how does it deform? So how does it happen that it goes to some general ensemble? That depends on how strong the integrability breaking is. That's the strength, okay? And by strong, I don't mean the coupling, because the coupling is just basically time scale. If its coupling is small, you have to wait long. The question is whether this scales in some particular way in the parameters, which is somehow anomalous in the coupling, which is depends on higher order or something. So, for example, we consider the boost deformation. We have this formula. We take the beta equals 2, which is the Hamiltonian. It tells me that if I take the Hamiltonian and deform it by an additional local Hamiltonian, which is just summation over one of these currents, which is generalized currents by some factor, and this should be a weak breaking of integrability. So what you do, you take the XXZ chain, great, and you take the third charge, here, alpha equals 3, okay, and we know that there's a current. The current looks like this. It's a little horrible, but that's how life is, okay. I hope this is right. I hope everything is right, because we had several misprints in this. Actually, we tried it from another paper, and then it was misprinted. Okay, I hope this is right, but it doesn't matter. You wouldn't read it anyway. Possibly, but I'm not a temporary lib expert, so that would never occur to me. Right. But, good idea. Okay. Yeah, maybe. You can try. I mean, any help would be appreciated, because I would like to try more of these, but it just, computation gets so heavy is that at some point we just gave up, okay? So I will show you what comes out, and I would like to do some more examples, and something that helps the computation is very welcome, because it just becomes very heavy to fix everything. So what we did was the following. We compared the strong and the weak integrability breaking of XXZ. So the strong one is just second neighbor interaction. Nearest neighbor, next to nearest neighbor interaction, and we call this operator ON, like next to nearest neighbor, and we add this with a coupling GN. And then the weak breaking, oh, there should be GJ here. Wrong. Another misprint. Should be another coupling here. Is just this putative weak integrability breaking by adding the summation of the third current, okay? And then the other thing is that you have to be careful, because these operators have some coefficient here, which is not yet manifest from the way I'm writing them, but I can take twice, 3 times, whatever. I need some independent definition of what the strength is. So what we do is that we take this operator and we look at the second, the standard Hilbert space norm of these operators. It turns out to scale linearly. That's easy to see in the volume, and we take this coefficient and we define an effective coupling which absorbs this coefficient, and then we get rid of this sort of manipulating the coupling by just renormalizing the operator. Then this is a definition of the coupling which is fine. And then, well, you have to test integrability breaking, so you just look around what you can have. Okay, let's look level spacing distribution, just standard test of quantum chaos. Okay, so you just look at, this is numerics now. So we take the energy levels of the system, we define the level spacing, we normalize them by the average level spacing, and then we know that an integrable moduli should have exponential distribution, non-integrable moduli should have Wigner Dyson. Okay, so there are some considerations to do, which I just quickly mentioned. That this is local chain, low energy spectrum, just quasi-particles. It doesn't show direct chaos, so you have to cut out the low energy part of the spectrum. Basically, you have to take the middle of the spectrum where this sort of very regular quasi-particle structure is eliminated, right? 1 particle, 2 particle gap, whatever, all these structures, you have to eliminate them. Not if you have an infinite chain with infinitely many degrees of freedom, because then they would just be swamped out by the statistics. But because I have a finite system, I have to cut out the part which is not modified by this. Then symmetries, because if you have symmetries remaining in your system, like translation, whatever, then your problem is that you have level crossings which have nothing to do with any integrability, just because they are coming from different sectors and they are not talking, levels not talking to each other. There is no level repulsion. So you have to eliminate symmetries. And then the other thing is that, so here are total momentum, spatial parity. We have to fix the total spin because that's also conserved. Okay, so that's, we fix it to be non-zero to eliminate the spin flip symmetry, which we didn't want to care about. And then what you want is a crossover. Actually, you perturb and you want to change this distribution to the Wigner Dyson, but that only happens instantly at infinite volume. In infinite volume, if you turn on a little coupling, integrability breaking, it just happens discontinuously. The finite volume, what happens is that you turn up the coupling and then you have to tune it, and there's a crossover which gets sharper and sharper as you go to higher and higher volume. I will show that. Okay, so there's a crossover value of this G effective, which depends on the volume, and this is what we are hunting on. So this crossover, I can show it here. So for example, we take HXXZ, the integrable case, 22, chain 22, and we always have nice exponential statistics for the level spacing. If we have non-integrable case, like the next to nearest neighbor interaction, or this other breaking, then sufficiently large couplings. I just show you sufficiently large couplings. We have a nice Wigner Dyson. Okay. So the next thing is that what we noticed is that if we have no breaking, we have exponential. If we have breaking, we have Wigner-Dyson. What happens in between is that the exponential is the peak at the origin, and this peak starts to move as we tune the coupling. It's basically what is happening is that you are getting an almost Wigner-Dyson, but the peak is in the wrong place. And it just travels as you change the coupling. And at some point, it arrives at the Wigner-Dyson. And we just say that the crossover happens when this is halfway. We just define the crossover coupling when this peak has done halfway the travel from the origin to the Wigner-Dyson position. And then we just define this crossover coupling. And so we plot the peak position as a position of the effective coupling. And we see that it really goes to the Wigner-Dyson value if we increase the coupling, and in higher and higher volumes that happens faster and faster. But you already notice a marked change, a strong integrability breaking, and that's weak. And for the strong, it really almost jumps to this value and then very fast goes there. And here you really see some hesitation before it moves at all, and then it's a very slower movement, okay? So what we define is that it should be 0.8, more or less numerically, square root 2 over pi. And we define that the crossover coupling is the coupling where the peak position traveled half the way, so it's 0.4 or something. And then what you do is that you plot the crossover, not the crossover scale, right, the crossover, what's written here? Crossover coupling as the function of the volume. That's a transparency that I already used, and I haven't noticed that I'm writing the wrong thing here. So what I'm plotting is the crossover coupling, different volumes. And so this is the crossover coupling, where I'm midway between exponential and Wigner-Dyson, and it depends on the volume. And this is the strong breaking, and that is the weak breaking. So this is the next neighbor interaction, and this is J. And you see that this happens very fast, already at small values of the coupling compared to this. This coupling is now normalized, so it makes sense to compare it. The strength is now really comparable. But also you see that this somehow becomes much faster, okay? And I'm doing here something which you shouldn't, but I did it anyway, is that I fitted a power law to this. Why you shouldn't fit a power law? Because I don't have a decade of parameter, okay? So it's a little cheating. But we fitted this power law not just in one example, but in many examples. And it always turns out what happens is that for the strong breaking, is critical coupling changes with some power B of the volume. And for strong breaking, this power is -3. So the critical coupling goes like L to the -3. This crossover coupling goes like L to the -3. And for the weak breaking, it goes like L to the -2. But actually, this L to the -3 was already known before, as I will tell you. And there will be some remarks on that. Well, this is when you are in the gapless regime. In the gapless regime, you really expect that these are power functions just because there's no gap. In the gapped regime, these should be exponential functions. So the log of the coupling should scale linearly with L. And then you see that these exponents are really, well, okay. There is a difference, right? Almost a factor of 3 between the two. So you can still see that the strong breaking is much stronger than J because this exponent is much larger. It really breaks integrability much faster in the volume. And here is something that I would like to understand, is that I don't think any other people understand at the moment, is that in the gapless regime, it is thought, this is also not understood. It is thought that the universal behavior for the strong integrability breaking is that the crossover coupling changes like scales like L to the -3. Okay, this was checked. Basically, you can't do much here. You just do numerical checks, exact diagonalization, whatever. Okay, but this looks like it's a universal behavior. These are the papers where you can look at it. This is only supported numerically, and it doesn't even depend on the space-time dimension. Okay, spatial dimension. So they check this not just for chains, but also for lattices, 2-dimensional, 3-dimensional statistical models. It's always the same. It doesn't even depend on the spatial dimension of the model. It's a very robust statement. Seems to be a very robust statement. So actually, the way we determined the crossover coupling was even different from theirs, and we still got the same exponent. So this is another argument that this is universal, because it shouldn't, if it's universal, it shouldn't depend on the prescription. You determine the crossover coupling, okay? But all results indicate that for weak integrability breaking in a gapless regime, we have a -2 instead of -3. So you see, it's weaker. It's weaker because it sets in much slower. It's even the exponent is different. So there is some real difference here. So, right, I don't understand any of this. I don't understand why this is free. I think neither do they. As far as I read their papers, there is no understanding. I don't understand why this is 2. Just would like to know very general numbers like come out from integrability breaking of this sort, and okay. And then basically, so this is the summary, and then so this is just what I told you, that there are basically 2 ways of deforming integrable models. So what I'm telling you, first, what I told you is that TTbar deformation of the IQFT and the long-range deformation of local spin change, they share the same algebraic structure. The reason they so similar, because this basic factorization identity of Zamolodchikov is also valid on the spin chain, and then you can just match the 2 structures together. Okay, then the deformations basically map the tangent space of the manifold of integrable models in theory space. I'm not saying we map all of the tangent space, but we map the quite large portion of it, because we have mapped an infinite dimensional portion of the tangent space. There could be other directions, okay? There's this novel factorization on the lattice, which connects the 2. Okay, there is this relation that I told you, which is relevant to GHD. And there's a novel class of integrability breaking, in the sense of, this is something I haven't seen before, weak in a different sense than you would all normally call weak. Normally you call weak when the coupling is small. It's not the coupling, it's basically the way it is breaking integrability. Order of breaking is somehow different. So the order at which it breaks integrability is different. This is weak integrability breaking, right? And the level spacing statistic shows that there is a real phenomenological difference between strong and weak breaking. And the question is really to get at the bottom of this. And these are my open problems. So my first question is, it would be interesting to map the full tangent space. As I told you, this is a huge part of the tangent space. Definitely not all of them. There's no claim that you mapped all possible deformations, right? As I told you, there was a way of satisfying the deformation constraints by choosing this X kappa deformation, but then there was just one way. Whether there are other ways, that's a good question. I don't know. Anybody knows, tell me if there are other ways. The long-range spin chains then. So as I told you, there's a problem with the UV completion of this TTbar deformation. But now we have the chain analog. So the question that naturally comes to one's mind, but that is again something that I haven't progressed too much, but maybe one can understand the UV behavior from looking at the spin chain picture, right? Because now you have this algebraic correspondence. Now you can try to make some sort of lattice analog of these theories and try to see how they behave in the UV, right? Because you would have some sort of regularized analog of these theories. It's actually something that's interesting. Then is how universal is this exponent 2 for weak integrability breaking? It turns out that Tristan McLaughlin and Spearing, they have a recent paper in which they took the ADS CFT spin chain with the 2-loop truncation, which is non-integrable. If you truncate there, then it's non-integrable. It's weakly chaotic in the sense that I told you, but they found -1 instead of -2. Okay. Seems that there are different classes. They argue that maybe the reason is that they have SU2 and in XX that we have only U1. I don't know if this is the reason, because otherwise the L to the -3 so generally didn't depend on any sort of symmetry, whatever, even space dimension of the model. So I don't know why the weak breaking should depend, exponent should depend on this sort of thing like symmetry or whatever. Then the question is that, is there a hierarchy here ever vacant between integrability breaking? So you can follow the manifold not to first order, order 2, order 3. Does this change the exponent? Is there a rule how the exponent changes? Maybe if we understand that, then we understand where the exponents come from. They're very nice exponents. They are just integer numbers, okay? They are not some, I mean, even the conformal filter exponents are too complicated compared to these, right? They are just basically integer numbers. No? And, well, I already said this, but I repeat, really the theoretical explanation of this universal crossover exponents, this eludes me completely. So anybody who has some idea on that, and welcome to solve this. I think that's all. So thank you for your attention. And my usual way, I didn't leave you time for questions, so ask questions now, because once I start speaking, it's very hard to stop me. Yes.
Yeah, there is a question I wanted to ask when the paper came out. So the reason why people consider these types of deformations, well, the local deformation was to change the dispersion relation, the relation between momentum and rapidity. So, for example, this is how you get this Zhukovsky map in ADS-CFT. And the bilocal deformation was proposed in order to get what is called the dressing phase, which is the most complicated part of the ADS-CFT beta-ansatz. So what you are seeming to imply is that the dressing phase is coming from a TTbar-deformation. So this would be very interesting.
That's analog of TTbar, yes.
Yeah. So there should be some. I mean, if we are searching for the spin chain or the theory which gives this ADS-CFT beta-ansatz, it should come from. Okay, local deformation is rather simple to reproduce, but this bilocal, if it's really just a TTbar deformation, this would be very interesting to understand.
Yeah, and as I told you, it's the factorization identity which is crucial in this. So yeah, that would actually you should make use of the factorization identity to do that. So that would be a very good first use of this identity which we just derived. Yeah.
Gábor, I have a terminological question in the sense that when you talk about a long range deformation, you mean non-local but finite range, or they can extend to infinite with some power law?
They extend to infinite. So what happens is that if you go to finite order in kappa, then these operators are basically still finite length. Well, you have to remember that actually in the integrable chain, the length of charge is actually dependent on the charge, and they are longer and longer charges as you go higher and higher. That's also true. But all of them are finite in support in finitely many sides. If you take the kappa deformation to higher and higher order, your charges just extend. And when you take it to infinite order, which you should do if you want to preserve integrability, right? You cannot truncate. Then they actually extend to infinite length. What happens is that they become this sort of quasi-local operator, which have what is called a finite Hilbert-Schmidt norm, and they also satisfy some other properties with local operators. There's a definition of quasi-locality, so that they are sort of local. Sort of local in a proper, I mean, they are not really local in the way of being supported on finite intervals, that they are still preserve lots of properties of local operators, which can be used then to make computations.
Then my question is, if they interact with a kind of power law, what is the exponent of this power law?
No, it's not power law, it's exponential.
Exponential.
It's
okay,
exponential,
so
it's exponential.
Not
yes.
local in this sense, it's finite range because it's exponential.
In that sense, it's, yeah, the exponential has a range, yes, yes,
okay.
But it still has a tail.
Okay.
Yes.
So I wanted to comment also in relation to what Irina was saying. I guess I should point out that some of this discussion of long-range deformation of spin chain was also independently worked out in a paper by Enrico Marchetto, Zhu Yang, and myself, which I think appeared maybe one day before yours.
Sorry, I'm not really familiar. So sorry.
Yeah. That was more inspired by ADS-CFT, and in particular by this very simple dressing factor that appears in ADS-3 at pure and SNS, which I flashed on the last slide yesterday. But in any case, it's like the simplest part. The issue in trying to reproduce something like the ADS-CFT dressing factor is that it contains an honest TTbar part, which really has this non-local feature. It goes like essentially momentum times energy. It's something that really comes out, for instance, from light gauge. And you cannot really use among the many generators, you cannot really use in a spin chain the momentum. You have the Hamiltonian, of course, but you don't have momentum. You have, of course, the shift. And that makes the thing even more non-local in a sense, because you have to use essentially the log of the shift, whatever that means. And we never really managed to, to nail down how you can introduce a dressing factor in this way because of this non-locality. Yeah, I don't know if you ever maybe consider like this particular issue of trying to put the momentum really like in TTbar, like some P0 as generator in a spin chain. We tried and failed, I must say.
No, I didn't, because that's not really my direction. So I was more interested in the spin chain, on the spin chain side, and quenches and integrability breaking, right? But yeah, I just posed this as you must know much more about what was the actual relevant question here. Yeah. Yeah, that's right.
Yeah, so I have a question about what you write in point 2 there. So if you can you expand something, because that sounds interesting, but I guess that you probably would need to consider finite length spin chains in order to actually answer that, because these kind of UV behavior, this weird discontinuity.
Not finite length, finite lattice spacing, you mean?
No, I mean finite length. Because the point is that the effects that are interesting in the UV for TTbar and for these kind of deformations, you see them on a cylinder. So you actually need to account for wrapping corrections. I would guess. I would guess probably that's where, because I mean, my question is, do you see any kind of thing that might remind you of what you see in the continuum theories?
Not yet. This is really very much a half-baked idea of saying that you have a lattice structure which is now similar to TTbar. It's lattice. So why not think about the actual thinking of making a corresponding lattice regularization of the TT? But this is just really like, you look at it and it suggests itself. But I agree, the wrapping corrections could really spoil the game. I'm not sure they do.
No, but maybe looking at that, I don't know if it's possible, but maybe looking at them on a lattice will kind of explain what's going on in the UV. I don't know. Maybe you can control them. That's something. I don't know. We can talk about that if you're interested.
Okay.
Yeah, and I have another question, if I can. So it's actually it's about the first step. So you claim that you do not map the full space, right? But if I'm not wrong, Sasha Zamolodchikov said that these kind of deformation map the full space.
Singe-Gordon case, probably they do, but I think even that is, I consider that as an intuitive statement.
Yeah, so well, I think its argument is that if you start with a minimalist matrix, then you can generate the full CDD space. So you essentially have all the S matrices that you want.
Yeah, but maybe there are also non-CDD deformations of the S matrix. So you can imagine that there are deformations of the S matrix. Once you give up locality, for example, then you might have these more easily. And I don't know. I wouldn't make the statement we have mapped all. I'm just
just on the safe
disclaimer here, very fine point that I wouldn't make that statement.
All right.
Yeah.
To follow up on this very point, I think that the statement is that if you want a CDD that is regular and periodic, these charges, they give you a basis essentially for that space. Yes, it's essentially the Fourier transform basis, and I think it's a general statement. It's just an analyticity. Then if you relax some analyticity, then you can get more. But I mean, you can make precise exactly which space they characterize. Yeah. Then I think it's it's pretty general. Then of course, if you have poles and you introduce more bootstrap, more states, it's more complicated.
I'm interested in this continuum limit of your spin chain. So although, you should consider infinite size spin chain, but if you consider also lattice spacing goes to 0 limit, then the continuum size can be finite.
Yes.
And then introduce certain like a DDV-like regularization.
Whoa.
And then you can consider some massive theory. And then maybe this long-range spin chain is related to really TTbar or TTbar.
That's what I was just thinking 2 days ago. If you think about the XXZ regularization of Singe-Gordon, then maybe you can try to match it there. This thing that I told you about, exactly. But it's still just, a vague idea, right? It needs to be, one needs to sit down and see whether there are any obstacles in the way, right?
So in your discussion, you used the level spacing. So people also use the other, like for example, OTOC, like out of time correlator, and the Lyapunov behavior to study the transition. So
yeah. So for example, these guys use
yes.
something completely different. The guys there used basically there's an intermediate distribution. I forgot how it's called. Something with B. I'm sorry, it just escapes my mind. Brody, the Brody distribution, right? The Brody distribution has a parameter and it interpolates between exponential and it has a parameter. They do that parameter, and then with that parameter they follow the crossover. But they get the same exponent as we do, so at least this exponent is really something universal, even from that perspective. And you can also do other things. This just occurred to me, right? So I didn't look at this anywhere. It just sort of occurred to me that if the maximum is moving from the 0 to this 2/pi position, then okay, so let's just follow that. It's just a quick idea, and it worked, okay. But yes, there could be other ways of doing it.
I see. Thank you.
But it was actually good that we did the other way, because at least we saw that this -3 is also independent of the prescription. At least, well, there is another prescription that gives you the same exponent for the strong breaking.
I see. Thank you.
Because even the universality has to be argued here, right? There is just numerical evidence for everything of these exponents, nothing better.
Another